Professor?
Yes.
Yeah, actually, that was the one question I had too. That one, and I think the first line you wrote, is that in reference to question one of the multiple choice where there's two identical answers?
That doesn't matter. If there are two identical answers, one of them will be correct. That's fine. Not a problem. But this was a little bit of a, the question is not wrong. The answer was supposed to be 80 moles.
Perfect. That's what I thought. Okay, good.
Okay. So that's what I have to say about the exam for right now. I have not corrected it. A nitrate is any compound with nitrate ion in it. A carbonate is any compound with carbonate ion in it. So calcium carbonate is a carbonate. That's how we say it. Okay. So we go to the unit right here. Energy and work. And I'm going to go back into it one more time, third time maybe. Energy, ability to do work. Move an object with the use of force. That's what ability to do work means. Work means moving an object with the use of force, or changing the acceleration of an object with the use of force. That's a better definition. Work is defined that way, and in chemistry, we are only concerned right now with one type of work. That's change in volume when the pressure is constant. And that work, therefore, is called P delta V work. And P delta V work equals P delta V, but if the work is done on the system, the sign should be positive. When the work is done on the system, the volume of the system decreases. So the sign of V is negative. Therefore, we have this situation here, W, Q plus W, E equals Q plus W, but delta E equals Q minus P delta V, because W is always negative P delta V, because volume has opposite sign than work. Enthalpy, heat of reaction, standard heat of reaction, standard enthalpy of reaction, all those names are one and the same thing. It is very rarely, but sometimes also called QP, meaning heat produced at constant pressure. That equals that, and then we have the equation for delta H. Delta H is enthalpy of the reaction, heat of the reaction. And we have many different type of reactions. So instead of writing reaction, we can write heat of neutralization, heat of combustion, heat of gas formation, heat of formation. And what is heat of formation? Heat of formation is forming 1 mole of a compound from its constituent elements, meaning the elements that are making up that compound. So for water, hydrogen gas and oxygen gas are the compounds that are making up water. And when we are talking about this heat of formation, we also mean forming 1 mole of a compound from its constituent elements in their natural state at 25 degrees Celsius. And so we have to define what our natural state is. For oxygen, the natural state is 25 degrees Celsius is O2 gas. So we need to write that down in the equation. So here we are writing down heat of reaction for forming 1 mole of CO2. Carbon is taken as graphite. Carbon also comes in form of diamond. And we are not talking about that form of carbon. We are talking about carbon graphite. Carbon also has another form. They are called allotropes. Diamond and graphite are 2 allotropes of carbon. You don't need to remember that name. And there is a third allotrope of carbon also. We won't talk about it right now, but we have to specify at 25 degrees Celsius that element in its natural form. What does that mean? O2 in its natural form at 25 degrees Celsius is a gas. Carbon dioxide in its natural form at 25 degrees Celsius is a gas. So that's what we write down. So that's the heat of formation. That's what it is. And we call it delta H superscript 0. And superscript means 25 degrees Celsius. That's what it means. That's the main thing we need to remember. Nobody tells you that. You have to remember that superscript 0 means 25 degrees Celsius. So this standard heat of formation of all the compounds is given in a table. All you have to do is to have your smartphone and ask for standard heat of formation table, and that's given to you. So you need to be a little bit familiar with that. It's very simple table, not much to it, but just know what to do. It starts with what substance first? Aluminum, because it starts with A, B, C, D. So if you're looking for water, you will want to look under hydrogen and H2O. If you are looking for carbon dioxide, you would want to look under carbon. So that's how it works. And you also remember that elements don't need to be created at 25 degrees Celsius. They are already there. Compounds are the ones that are created by chemical reactions. Elements are not created by chemical reaction. Therefore, the heat of formation of all elements in their normal natural state at 25 degrees Celsius is 0. And nobody tells you that. You just have to understand that or remember that. Now, in the table, Often they give you that, or they may not give you that because they are, everybody says, of course, it has to be 0. Now, heat of reaction is a state function. Therefore, in order to calculate heat of reaction, what we do, of course, if it is a state function, we say final minus initial. This is how we find final T minus initial T. For example, initial T. If you are talking about delta T, the change in temperature, delta T equals final T minus initial T. So because this temperature is a state function, we just have to subtract final minus initial. The delta HF is a state function, so what do? We subtract. What do we subtract? But what do we use to subtract? That's what heat of formation, that's what we do. We use to subtract. Heat of formation of all the compounds as the product minus heat of formation of all compounds that are the reactants. So final minus initial. So heat of reaction. Heat of reaction. Delta H reaction equals sum of, this is sum of. This means sum of. Everybody knows that. I'll write it down anyway. Sum of the heat of formations of all the products minus sum of the heat of formation of all the reagents. That's how we calculate the heat of reaction. And heat of formation is found in the tables. So this is a very simple thing.
Professor, I just joined a little late. What chapter, what unit are we on?
We are on unit 22, energy and work.
Thank you.
And everybody, if you join in late, no need to be in the dark. Instead of that, ask like this person did. I joined late, and what is going on? That's a good thing to do. Okay. So here we are. Enthalpy, and then state function, and then heat of formation, and then heat of reaction, and how heat of formations are connected with heat of reactions. That's what we are talking about. And there is a simple equation that is used in order to calculate the heat of reaction. And the heat of reaction is calculated the way you write the equation, however you write the equation. What do we mean by that? You remember that now we are allowed to write an equation with fractions. So that's, sometimes we write that with fractions depending upon what is expected of us. And then we would calculate the heat of reaction accordingly. So let's see. Here we are. Heat of reaction. This is the equation for heat of reaction. It is a simple equation. If you understand it, you will be able to write it down very easily. Number one, the heat of reaction is a state function, and therefore final minus initial is how you would calculate it. And the question is, what final or what initial? The final is the product. We are talking about a reaction. What is final? The products are the final. What is initial? The reactants are the initial. So final minus initial, meaning final something of the product minus something, minus initial something of the product. minus something of the reagents. That's what it means. And what this something is, heat of formation. And where is heat of formation found? In a table that is available to you all the time. So that's what it is. So let's see now. We are going to think about work now again. And how do you measure work? How would you measure if you do 10 push-ups? How much work have you done? How much work do I do when I do 10 push-ups? 20 ups and downs. 10 push-ups means 20 ups and downs. Putting my palms on a scale while doing push-up shows 100 pounds. So that's what I did. I got my scale. I got on my palms. I put my palms on my scale. I looked at the scale. It was 100 pounds, showing 100 pounds. Okay. That's not my weight, of course, but the weight that is I'm supporting on my palms is 100 pounds. That's what it means. And that's what I'm interested in. The vertical distance moved is 0.40 meter. This is what I measured again. Little more than a foot. How much up and down I'm going. Assume same amount of energy usage from pushing up and pushing down. Work equals mass multiplied by delta G multiplied by vertical displacement. Now, this kind of problem I'm not going to ask you in the exam or any place. But it's good for us to understand that it is possible to calculate what work. A simple thing like a push-up, you can calculate it approximately, of course, but nevertheless, it can be calculated. And this is how you calculate it. G is the force of gravity. So mass is 100 grams. Convert that 100 grams into kilograms, 45.4 kilograms. Vertical displacement is 0.4 meter, that's that. And gravitational constant G is 9.8 meter per second square. So that's gravitational constant. When we calculate that, it comes out to be kilograms per meter square per second square. Those are the units. Write your units all the time. Write your units all the time. Please, please, please. All right. So here I have the units. And these are the units of work. And these are, of course, the same thing as joules. And I made that into kilojoules. So this means joules. Kilograms per meter square per second square equals joules. Joule is a composite unit made up of many units. And this is something I would give you in exam also if I'm interested in, if you need to deal with this, kilogram per meter square divided by second square, I would tell you that 1 kilogram multiplied by meter square divided by second square equals 1 joule. I'll tell you that. So you don't need to remember that unit. We deal with the units of joules. We don't deal with the units of horsepower or British thermal units or anything like that. We want joules. And that's, if you need to convert that into something else, I would give you the conversion factor. Okay, so when this was done in the classroom, I would actually do 10 push-ups. Today, I'm not gonna do that. Yeah, I can't show off, because you won't be able to see me even if I do my push-up. So what's the point of doing the push-up when I cannot show off that, yeah, in my old age, I can do 10 push-ups.
I say everybody should do 10 push-ups just for an experiment.
Okay, everybody who feel like doing 10 push-ups, do it right now. Go ahead.
And we get 5 extra points.
You are being generous. You did not ask for 10 extra points. I appreciate that. So this energy went out of the system, out of your body. So it's negative. And of course, cos theta is -1. Cos 180 is -1. So this number works out to be negative. And that should be negative because it is energy going out of our system. So this is the calculation. Once again, I'm not going to ask about this problem again, but I just want you to see that it is possible to calculate simple thing as how much work is done when you are doing the push-up. All right. Approximately, of course, but nevertheless, yes. Okay, I hope you're done with your push-ups because we are going to go to the next thing. Calculate Q, the heat released when 1 tablespoon of sugar is burnt or digested. Burning and digesting is the same thing. Really. That's why sometimes say, oh, my stomach is burning. I need to burn up some energy. That's where it comes from, because digesting and burning is the same thing. Digesting, what is the difference then? Well, of course, we are not burning. There is no fire. The fire in my belly, we also say that. Of course, there is no fire in the belly, but there is. What do we mean by that? That means that the reaction that is going on in the belly, when we add up all those reactions that are going on in the body, at the very end, they look like combustion. So sugar, if you burn sugar, the products are going to be carbon dioxide and water. And when the body is done with that sugar molecule, the products are also carbon dioxide and water. So body is burning something, so to speak, quote, burn on, unquote, very slowly. And why is that? Because that's the way to extract energy from this reaction. The energy that is coming out of this reaction, the body extract that energy, and that's the energy that we use in order to whatever we want to do. So, all right. 1 gram of sugar is 3.9 food calories. 1 food calorie equals 1,000 small calories. And 1 small calorie equals 4.184 joules. So joule is a very small unit of work, of energy. So we have 1 gram sugar, 4 grams sugar is in 1 teaspoon. 1 gram of sugar is 3.9 food calories. And so when we do this, answer comes out to be negative 65. Let's do that. Simple thing.
I have a question. So I did the equation and I got positive 65. Why do you switch it to negative?
Because sugar is burned. So did the energy go out of the system, or did the energy come back in the system?
Go out.
That's why negative.
Okay.
The money went out of your pocket, so that's negative.
Okay. So every time I'm solving for sugar burn, then I have to change the answer to a negative instead of leaving it positive.
That's right.
But would it be incorrect if we did leave it positive?
Yes.
Okay.
That would mean the energy went in the system. That's incorrect, right? So.
And would you mark the whole problem as incorrect, or
no,
only
I
take
wouldn't
some points off?
mark the whole problem. If the problem is 4 points, I might take off 1 point.
Oh, okay.
No, I mean if you do something right, that counts. The final answer is not, life is not about the final answer. Life is about doing all those little things, and they add up. So I also add up. Okay, so that's what we do. 4 grams of sugar. Sug multiplied by, convert that into 3.9 food calories. So 3.9. So I'm just gonna say 3,900 small calories. Cal divided by 1 gram sug, and then multiply that with the other conversion factor, which is 1 small calorie equals that 4.184 joules divided by 1 small cal. And then we get the answer, and we'll write it down -65. And now we are only going to do 2 kilojoules. We're going to convert that into joules into kilojoules and all that. You know how to do, so that's fine. Now, how many push-ups burn up 1 teaspoonful of sugar? So talking about burning energy, and those of you who are interested in weight management, well, this would be a question. And a lot of people these days are interested in weight management. So how many push-ups burn up 1 teaspoonful of sugar? So how much sugar should we be eating? Is sugar, what kind of energy, what do we call it? Energy, the word is not coming to me right now, but anyway, energy budget we have. So how much sugar should we be eating? And people are telling us all the time, eat less sugar, at least less sugar. So let's look at it from the point of view of chemistry, or how much work, how much energy is in 1 sugar, and how much energy is used to burn up. I mean, how much energy is needed to do so many push-ups, and compare those two. That's what we are doing now. So how much push-ups burn up 1 teaspoonful of sugar? 180 push-ups are needed to burn up 1 teaspoon of sugar. Sugar has a lot of energy, so to speak. And you can do the calculation yourself. I'm not going to ask you this question. But anyway, it's a simple dimensional analysis problem. 10 push-ups equals 3.6 kilojoules. Okay. Example 7. 65 kilojoules heat is released. That's why I did not write negative, because I say released. Otherwise, I should have, if I don't say release, is exchange, then I would say negative. Maybe it's better to write exchange instead of release. Release is kind of confusing. It is exchanged. And then I would say negative. The heat exchange, heat exchange by burning for is negative 65 kilojoules. Now I can put in negative 65 kilojoules. Calculate heat of combustion. Heat of combustion, the reaction of burning of sugar. Calculate heat of combustion of sucrose. 1 mole of sugar is 342 grams. And for those who wants to know the what do we call it, the formula of sucrose, I will not ask you what the formula of sucrose is, but the formula of sucrose is right here. C12H22O11. That's the formula. You are not responsible for that formula. So, what is the heat of combustion of sucrose? We need to write down the equation. 1 mole of sucrose is burning. It's going to require 12 moles of oxygen. When it burns, it will make 12 moles of carbon dioxide and 11 moles of water. And this is what we are talking about. The heat associated with this equation is the heat of combustion of sucrose, burning of sucrose. And 1 mole of sucrose what happened here? Something is strange here. There are no numbers on the top here. Here. 1 mole of sucrose multiplied by 1 mole of sucrose, and then 342 grams, it should be over here. That's what the thing is. This gram should be over here. So I will write it down again and say 342 gram sucrose. Okay, that's better. Mm, 4 grams of sucrose is negative 65 kilojoules. That's what we know from our experiment. And therefore, this is the heat of combustion of sucrose. This result, negative 5.6 multiplied by 10 to the 3 kilojoules moles sucrose per mole of sucrose can be reported in 2 ways. You can write it down as the equation. You write down the equation, and for this equation, burning 1 mole of sucrose, we have heat of combustion equals negative 5.6 multiplied by 10 to the 3 kilojoules. Or we can write that down in the equation because heat was produced, so it's a product. So we can write that down in the equation as a product. And if we are writing it down as a product, that's going to be positive number here. It's not going to be negative. I write here number 2. This is where we are writing heat as a product. We will be writing it plus this many kilojoules of heat. And this is an exothermic reaction, of course. That's what this means, because product is positive. The heat is positive as a product, and therefore delta H reaction is going to be negative, and that's that. If the coefficient in the equation are multiplied by 2, heat of combustion also multiplies, doubles. So if instead of writing the equation as 1 mole of sucrose, we write it as 2 mole of sucrose, which normally we would not do because we like to write equations with the lowest common denominator as the coefficient. But sometimes we may want to write the equation like that, and there will be some once in a great while there is a reason to do that. Then all we have to do for this particular reaction, the heat of combustion is 2 times that of this equation. That's all there is to it. Because heat of combustion is part of the stoichiometry. It's in the equation itself, it's part of the stoichiometry. And therefore, if you multiply this by 2, then the heat of combustion, everything else multiplied by 2 across the board. And so heat of combustion is also multiplied by 2, and that's what the multiply by 2 looks like. Example 8. A flask toppered with a balloon contains magnesium ribbon suspended on top of HCl aqueous. This system is changed by letting magnesium and HCl aqueous react. This is how the system changes. Write symbols of 4 properties of the system that change due to the reaction. So you're going to tell me. So let's start with Diego. Which one of the 4 properties got changed? Can't hear you. The question is, which one of the 4 property got changed because this reaction happened, magnesium and HCl reacted? The system is flask toppered with a balloon containing magnesium ribbon. And then the reaction happens. This is our system. What got changed of the system because of the reaction? 4 properties got changed. Which are those? Temperature got changed. Very good, T. Now, America, another property of the system that got changed. America, Say hello. America, well, anybody, please, if I ask your name, at least say hello, if nothing else. And if you don't say hello, I take it for that you have gone someplace else for some reason. Okay, Alexander.
Pressure, volume, and mass.
Very good, volume. Volume got changed because it was like that before, and afterwards it will be like this. So volume got changed of the system, very good. Now, this system, did mass get changed? Did anything went out of the system or came in the system? Anoti Daise, did anything go out of the system or came in into the system? Anoti Daise is not there. Maybe I should write this thing, start writing down who is there and who is not there. Ethan?
No, the mass doesn't change.
Can't hear you.
The mass doesn't change because nothing leaves.
Yeah, nothing got changed. The mass did not go out of the system. So this system is, what type of system? Is it a closed system or is it an isolated system?
Isolated.
Isolated means it's not gonna even let the energy go. But so for the moment, for 1 second or 2 seconds or 10 seconds, we can say it was an isolated system, and that's fine. We can presume that. Okay. That even the energy did not go out of the system. It got hot, but the system for that particular moment, no energy went out. Pretty close to true. Not quite true, but close to true. Okay. Now, let's see. Lisa, what another property of the system got changed? Lisa is not there. All right. Makaya?
Pressure.
All right, let's think about pressure. That's one possibility, that pressure got changed. P. And pressure got changed of the system initially because hydrogen gas was produced. But this hydrogen gas was able to expand the volume, expand the balloon, and therefore the pressure got equalized. So initially, when the reaction happened, right away the pressure got changed, but the pressure change was equalized by changing the volume. So the pressure stayed the same, about close to 1 atmosphere pressure. So this is a little tricky one. True, pressure got changed in the beginning as soon as the reaction happened, but then very soon the pressure got equalized. So if we say volume got changed, then we are not going to say pressure got changed. If we say pressure got changed, then we should not say volume got changed. But because we said volume got changed, we are not going to say pressure got changed. So now, what other property of the system got changed? Okay, everybody, the new property that we have been talking about, delta E got changed. If the temperature got changed, then delta E got changed, definitely. And what else got changed? If the volume got changed, what else got changed? Work. And if delta H got changed, what else got changed? Okay. Or we can say Q got changed. So those are all the properties. All the properties got changed. Work got changed, Q got changed, delta E got changed, V got changed, T got changed. All changes that happened. So also put the property or function of the system. Now we know about new functions of the system like work, delta E. We also know about H or enthalpy. Those are also functions of the system. So you are also going to start thinking about them when you are going to think about what got changed. Example 9a. The heat capacity of a calorimeter is 33.0 joules per degree Celsius. Now, you guys, please look very carefully at the units. The units are going to tell you what you are supposed to do. Heat capacity is different than specific heat capacity. Specific heat capacity is small c, and the units are gram joules divided by gram degree Celsius, or joules divided by Kelvin if you want to write it that way. Whereas heat capacity is joules divided by degree Celsius, no grams in there, because this is a heterogeneous substance. And we cannot talk about grams in a heterogeneous substance, because whose gram are you talking about? Calorimeter is made up of many things. Only we can talk about grams if it is a homogeneous substance. So heat capacity is different than specific heat capacity. And what is the symbol for heat capacity? Specific heat capacity is small c. Symbol for heat capacity is big C. Okay. Calorimeter is filled with 99.54 grams of dilute HCl at 20 degrees Celsius. 0.496 grams of magnesium limiting reagent, magnesium is a limiting reagent, is added to the acid. The reaction proceeds. So we are talking about the reaction that we just talked about it. Okay. Total mass after the reaction is 100.00 grams, but just adding the two masses. The temperature rises to 25.6 from 20 to 25.6. Specific heat of the solution is 4.2 joules per gram degree Celsius. Calculate heat exchange by the reaction with the solution and the calorimeter. So first thing I want everybody to write down is simple equation showing where the heat going to. The heat came from the reaction. The potential energy of the bonds, chemical bonds in these compounds was partially converted into heat energy. That's where the heat is coming from. So we can say that Q of the reaction, Q that happened of the reaction, because of the reaction, equals now this Q of the reaction is going to be negative or positive. Okay. America, are you there?
Is that QRX?
This is Q. Reaction. This is reaction. Q reaction. RXN stands for reaction, everybody. RXN stands for reaction. We don't write reaction the whole thing most of the time. Q of the reaction equals Where did it go? It went into the calorimeter, so it's Q cal. That's what we write, Q cal. And plus Q of the liquid. Now, is this Q positive or negative? Lisa, is this Q positive or negative? Ethan, is this Q positive or negative? Michael, is this Q positive or negative?
Positive?
Is the heat come out of the system or it went in the system?
It's being exchanged, so it's staying in the system, right?
Exchange, that is correct, with the surroundings.
Yeah.
Right. And what is the system? Tell me what the system is. What is the name of the system?
It's a open system.
When we say that it's an open system, yeah, we don't know. It's a calorimeter, so it's a closed system.
Okay.
We are exchanging energy, but nothing else.
Okay.
So closed system. Now,
Okay.
how would you characterize a system in chemistry? So the system is the equation. So we write the equation, and that's the system. Mg plus HCl aqueous. Yeah. Mg plus 2HCl aqueous MgCl2 plus H2. This is what we mean by a chemical system. A chemical system is represented by an equation. So this whole system, heat capacity, calorimeter, and everything is a system, and it is represented by this equation. Now, did the heat went out of the system or go in the system? Is heat a product or is he a reactant? Did you heat up it's a product. That's right. So it went out of the system. Product is something that went out. And therefore, this Q is going to be negative. This is negative Q. So whatever answer we're going to have is going to be a negative. So now we're going to do this Q cal and Q liquid and make that negative. Q cal, calculate the heat associated with Q cal. So here we have want heat. So what am I going to multiply this with in order to convert it into joules? This is a very simple thing. Heat has to be in joules. And the heat capacity of the calorimeter is given to me like that. So what am I going to multiply it with to convert it into joules? Even if you don't know anything else, you should be able to do this much.
Multiply it by Celsius.
Yeah, multiply it by Kelvin. And which Kelvin is it going to be? It's going to be delta T, of course, the change in temperature because of that. And delta T is going to be 20 degrees Celsius to 25.6. So I'm going to multiply it by 5.6. And this is going to be a negative number, of course, for Q. Delta T is going to be 5.6 Kelvin or 5.6 degrees Celsius. Everybody remember that, please. Delta T equals 5.6 K, which is the same thing as 5.6 degree. Oops, what happened? Oh, yeah, damn. degree Celsius. Shouldn't have done that, but anyway, there it is. Okay. I get rid of it. Once you write it down, I'm going to cut it. Okay. So that's delta T. I'm going to write it down over here. Clear. There you have 5.6K multiplied by 33.0 joules divided by Kelvin. That equals something. Oh, I don't like that again. I should not be doing that. Dang. 5.6K multiplied by the conversion factor. This is a conversion factor. Everybody can see it's a conversion factor. 33.0 joules divided by 1K. And then plus specific heat of the solution is 4.2 joules per gram degree Celsius. That's where the heat went. So I'm going to write down plus small c equals gram multiplied by delta T multiplied by Q equals, not C equals, Q equals multiplied by small c. And that is going to be a given 100.00 grams multiplied by delta T, same delta T as the calorimeter, because calorimeter and that liquid are in the contact with each other. So we assume that it's going to be same delta T, 5.6 K, big K. Kelvin is a big K, multiplied by 4.2 joules per gram multiplied by Kelvin. And now I'm going to cancel out all the units. You must write all these units and you must show me that you are canceling it out. So I cancel that out here. And then I change this and grams cancel out. Kelvin canceled out. And so I am left over with units of joules. Everybody sees that. This is what you need to show it to me, that you have the correct unit. And when you are adding these two up, it's going to be negative 2.6 kilojoules. That's going to be the answer. And this is a negative number because it's an exothermic reaction.
Professor, when we're typing it out, it's really easy to show canceling units on paper, but typing it out, it's kind of hard to do. How do you want us to show that the units are canceling out?
Well, is it possible for you to write it on your hand and then show and send a file to me?
I could probably do that. It might take a little bit more time just to upload it, but I could probably do that.
Well, that would be easier because then you are writing it and then you can show it to me. Also, some people are really telling me that it takes a long time to type it out in the computer.
It definitely takes a lot longer than it would on paper. That's for sure.
So then if you are writing on the paper and if you send that to me.
Are you sure you're going to be okay with that though? Because another time you said that if we send that in PDF, it's more difficult for you to grade.
It is
told us not to do it.
Grade, but that's another way to do it. Or you can do both.
I think I would just stick with one.
One way to deal with it. The other way to deal with it is not show me that. But as long as you have the right units and you see that in your, you can cancel it yourself, then I'm okay with it, okay?
Okay, that's perfect. I'm fair with that.
If you can cancel, if you can't cancel it, you have a problem. If you wrote down something that you cannot cancel, I'll be able to see it easily, and then I'll say, oh no, that's not right. So, okay, if you're printing it out, then don't cancel it. Example 9, use the answer from 9a to calculate delta H of reaction for Mg plus 2HCl, MgCl2 plus H2. So this is what, negative 2.6 kilojoules. Now this is Q, this is not delta H. So what is the difference between Q and delta H? One more time. Q is the heat released in an experiment, and we are using grams of a substance. So Q belongs to grams. Delta H belongs to moles. You know how to convert from grams to moles, so there is no big deal. That's what you do. So your Q, this here, is going to be Q equals negative 2.6 kilojoules. That is what you are going to use to convert that into this delta H. And delta H, of course, is for 1 mole. 1 mole of magnesium is reacting. And here I had 0.496 grams of magnesium, and that's the limiting reagent. So 0.496 grams of magnesium equals this many kilojoules of heat. This is our conversion factor. And we talked about this before. I'm talking about it again because I think this part is a little hard for student to grasp. This is a conversion factor. What is the given quantity? Given quantity is 1 mole. So I'm going to say 1 mole. 1 mole of Mg. And then I do the calculations and I get these answers, 1.3, negative 1.3 multiplied by 10 to the 3 kilojoules. That's the heat of reaction for this reaction.
Can we just walk through it just to be safe?
So what do we do here now? What is the next step? Delta H. What are the units of delta H? Is energy. What are the units? Anybody? Nobody wants to talk today. Many people not want to talk today. It's a bad day, bad hair day or something. All right. Come on, tell me what is the unit, what are the units of delta H?
Is it joules?
Joules or kilojoules, right. So that's what we are looking for. And we want to know how many kilojoules are associated with 1 mole of magnesium. We know that this many kilojoules are associated with grams of magnesium. So how are we going to do this? How are we going to get for moles of magnesium? Well, we need to
turn moles into grams.
Grams into moles, that's what we need to convert. So we can say for negative 476 grams of magnesium, convert that into moles. There is our moles. Everybody knows how to do that. And that many moles equals negative 2.6 kilojoules. So let's do the calculation here. 0.496 divided by 23.4. That many mole is 0.02120. Oh, 12. Okay, 360 mole. And this many mole Mg equals negative 2.6 kilojoules. And I have 1 mole of Mg. So I'm going to go over here now, multiply that with this conversion factor. And negative 2.6 kilojoules divided by 0.0212 mole Mg. And the answer comes out to be negative 1.3 multiplied by 10 raised to 3 kilojoules. We'll do this again because I have seen that in the past that students have difficulty with this step here. Okay, we're gonna go to example 10 now. Oh, yeah, not much time. Okay. Write how Q differs from delta H and how to calculate delta H reaction from Q. You are going to do this because you have seen this. We just did the calculation. And we'll talk about this again actually today. So keep on moving from here. Example 11. Predict signs, positive, negative, 0, or positive or negative of functions of systems given in the table below. This is a system. Is 4C3H5NO33 solid going into 12CO2 plus 10H2O plus 6N2 plus O2. This is called nitroglycerin. Another name for nitroglycerin sometimes used is dynamite. So we are talking about explosion, dynamite explosion. When dynamite burns, this is what happens. You are not responsible for this reaction. Remember, you are responsible for reactions where you have 1 or 2 reactants and 1, 2, or 3 products. That's it. This is an unusual reaction. You are not responsible for it. Having said that, it says plus 5.678 multiplied by 10 to the 3 kilojoules. Look at that. That's a very big number. We just talked about the delta H reaction for the Mg plus HCl. And this is much bigger than that, 5 times bigger than that. So nitroglycerin explosion, you can imagine, of course, the heat produced is a very high amount. And therefore, delta H reaction is going to be positive or negative. And we're going to start with who this time? We're going to start with...
should be negative, right?
Very good. It should be negative because the heat is coming out of the system, negative. Yeah, everybody is writing this down right now. Negative. Now, if delta H reaction is negative, what is delta E? Energy came out of the system or went in the system?
Out.
Out, so that's negative. Delta V, what would happen to the volume of the system at constant pressure? Explosion, what happens to the volume? Positive or negative or no change? Yes. What happens if an explosion happens in a room? Blows up, what does that mean? It increase the volume, right? Yeah. So delta V is going to be positive. And work was done by the system or done on the system? By the system. System blew up, blew up the whole room. By the system did it. So that work is going to be negative. System got tired. And of course, if delta V is positive, work is negative. These two are always opposite to each other. And these two are always same because both of these are energy. Okay, now let's look at B. This is an exothermic reaction. How can we tell? Because the product, heat is one of the products. Therefore, delta H is going to be negative. Delta E is going to be negative. Now we are going to see delta V is going to be positive or negative. We don't know. So how are we going to find if delta V is positive or not? Very simple thing. We are going to look at number of moles of reactants and number of moles of product of gases only. Why only gases? Because gases changes volume very much. Liquids and solid, their volumes don't get changed very much if the temperature changes. So when we think about changing in volume, we are only thinking about moles of gas, changing in the moles of gas. Now, at the same temperature, 5 moles of gas is a reactant and 2 moles of gas is a product. Which one, reactant or the product, which one is going to have bigger volume? 5 moles or 2 moles?
5 moles.
5 moles. Volume. Therefore, the volume got decreased because of this reaction. The volume got decreased, and therefore it is negative.
And so work is positive?
Then the work is positive. Don't even think about it. Because how did the volume got decreased of the reaction? The surrounding pushed the reaction mixture in. That's how the volume got decreased. That's why work is positive.
Okay.
Surrounding did the work on the system. And of course, delta V is negative, work is positive. Okay, C. Zn solid plus 2HCl aqueous, ZnCl2 aqueous plus H2 gas. Delta T is negative. I've given that to you. What does that mean? Is it a positive delta H or negative delta H?
Should be positive, right? Delta H, because the temperature went down. Oh.
Delta T is negative.
Doesn't that mean that the change in temperature?
Temperature is negative, therefore temperature went down. So that's going to be positive. And delta E is positive, of course.
Yeah.
Well, actually here I need to beg your pardon. I need to do something else. Delta E equals Q plus W. So we need to remember that. I am sorry. We need to go back here. If this W is positive and this delta H is negative, then delta E is going to be negative or positive. We don't know which one it's going to be. So my mistake here. It is negative or positive or negative, this one here. Positive or negative. because work is positive here. So we don't know which one is going to win. So we have to say it could be either one. Now we're going to wait for this one here. We're going to write down what happened here. I have 1 mole of gas produced, no mole of gas as a reactant. So the volume of the system increased. So V is positive. Everybody getting that? This is a simple thing. We are only going to compare the moles of gas as a reactant and the moles of gas as a product. There are no gases in the reactant. There is 1 mole of gas as a product. So the volume increases because of increase in the moles of gas.
That makes sense.
Because volumes of solids and liquid stays pretty much constant and a very small volume. But volume of gases, is very big. And that's why we do it that way. So this is positive and that too is to be negative.
So delta E is positive or negative.
Right. And so then delta E is going to be, this is Q is positive, heat is positive, Q and delta H is the same thing, and W is negative. So this is going to be positive or negative. Cannot tell which one is going to be. Okay, heat plus, so heat is a reactant now. That's what that means. Heat plus NH4NO3, solvation. What does solvation mean? Means dissolving. So we are dissolving ammonium nitrate. Ammonium nitrate is a substance, when you dissolve it, the temperature decreases. It takes heat from the surrounding and the temperature decreases because of that. So if the surrounding of this reaction, this is not a reaction, this is a process, a physical process. If the surrounding of this process is your knee that was hurting, and the doctor said, put the cold pack on the knee, then you're going to put the cold pack, which has ammonium nitrate solid in it, and you break the thing inside the container and the water outside, and there is a little pouch that you break, which has ammonium nitrate solid in it, and now it is going to dissolve in the water that is in the outside of the pouch, and this outside of the pouch is in contact with your knee. It's going to rob heat from your knee, and the knee is going to get colder. This is how it happens.
So then delta T is negative in this case too.
And the delta T is going to be positive because heat went into the system from your surrounding, from your knee. The heat went into the pouch.
Okay.
That's why your knee is feeling cold. So delta T is positive.
Okay.
And if the delta T is positive, then what is going to be delta H? The heat went in the system, right?
So it should be negative.
Now, solvation, what does that do to the volume? Let's talk about delta V now. What did it do to the volume? Before that, you had a solid, and the solid, the ions are together, and they are in a very little bit of volume. Once the ions are dissolved, they are in a much bigger volume. So the volume got increased somewhat, not as much as the volume increased because of formation of a gas, but by dissolving a compound, you are increasing the volume that all the ions can go into, all the ions can travel. Therefore, the volume is positive here. And if the volume is positive, work is going to be negative. Now we can say, okay, this is positive, this is negative, therefore we don't know positive or negative. The last one. 2N2 plus 5O2, 7 moles of gas, plus 22 kilojoules. Oh, this is an endothermic reaction. So delta H is going to be positive again. And I have 2 moles of gas, 7 moles of gas to start with, 2 moles of gas to end with. The volume decreased here. So work is positive. And this is positive and this is positive. Therefore, delta E is going to be positive. Q is positive and work is positive. Q plus W is going to be positive. So delta E is going to be positive. Okay, any questions? Uh-huh. When delta H reaction, meaning there is no temperature change. Number one, right? Then delta H reaction would be 0. Q would be 0, no temperature change. Now delta E would be, if there is no change in volume, then the volume would be 0, and then work would be 0. So that's when it would be 0, when there is no change in volume and there is no change in temperature. What type of reaction is that? That's another good question. What am I going to give you where a reaction happens, but there is a chemical changing that is happening, but there is no, and that is called a reaction with 2 arrows. So when we have something like this, a weak acid like HC2H3O2 aqueous plus H2O, so that's aqueous, that's why I'm not writing aqueous. And this is a dynamic equilibrium reaction. We have talked about dynamic equilibrium. What does that mean? That the reaction is going back and forth and there is an equilibrium. If 1,000 of these two coming together to form the product, then 1,000 of the product are going back to this to form from the reactant, and there is no net change in the concentration of the reactant or the product. So it's going to be H3O1 plus C2H3O2 1 negative. This is a reaction where there is no change in the volume and there is no change in the temperature. So this is where it would be 0. Okay. Good question. I like that question. Okay, we have a little time, very little time. Example 13a. Write the equation showing formation of 2 moles of ammonia gas from its constituent elements. The delta H reaction for the reaction, we're just going to write that equation and we are done for this part. So formation of 2 moles of ammonia gas from its constituent elements. Well, N2 gas, I have to write the states plus 3H2 gas and 2NH3 as the product, gas as the product. The delta H of this reaction is negative 92 kilojoules. So you can write it down plus 92 kilojoules because now I'm writing it as a product in the equation. So I write down plus, but the delta H of the reaction is negative 92. So this is how I will write the equation. And that's where we are stopping. And I heard you last time. So let's have that 30 minutes break and we will have a little shorter, what do we call it? Lab stuff. That's what we will do. So we'll still get out at 4:40. But I thought about it and I said, okay, yeah, let's get a little bigger break because you seem to be needing it.
I think the exam was taxing.
So we will meet at 1:50, half an hour of break.
All right.
And if anybody has any question right now, I am available right now. I'll come back about 5 minutes early. So you can also ask me question then. So everybody, one more time, half an hour of break.
I think my problem with this unit so far, Professor, is it just seems like the introduction of a lot of elements, and I'm still not entirely sure. I think I just need to practice with it because I'm not.
You have hit the nail on the head. That is correct. There are a lot of different things that are happening that are new. And that's one of the problems. It's not that you cannot understand it. It takes a little time. And as you pointed out, a little practicing in order to do that. Those two things are needed. That is correct. And we're going to do more of that in the lab today. So I'm going to provide you with that time for practicing.
Sounds good, Professor. Thank you.
All right. And that's why you may have realized that I'm repeating myself. Started again with work and with energy again today, because I understand what you're saying.
Yeah, I think with time, and we just keep doing practice problems and build a better understanding of it as a whole.
Right. Yes. Oh, yes. Okay. Now I'm going to stop the share and turn off the
The recording has stopped.
All right. So, Gonzalez Soto, are you there? Any questions? Okay. What about America? Any questions? America, are you there?